Okay, so what I want to do today is we talked about the equations of lines. So now what I want to do is I want to do equations of planes. And the idea is when you do Calc 1, I'll give you some function, then locally near a point, you can approximate the function by the tangent line. There are two ways of writing the derivative. You can write the derivative at some point A is the limit as h goes to 0 of f of h, a plus h minus f of a over h. Or you could write it as f prime of a is the limit as x goes to a of f of x minus f of a over x minus a. And the more interesting one is the limit as h goes to 0 of f of x minus f of a minus f prime of a times h over h equals 0. So when you look at the last, what we really have here is we have f of x minus the quantity f of a plus f prime of a times h. This is basically where you start, right?
Yeah.
This is your speed at start, and this is the elapsed time. So what we're really doing here is this is the tangent line approximation. So if we think about what's going on at this point, if this is the x coordinate a, what's the coordinates of this point? It's a
0.
well this is the curve, y equals f of x. So what would be the value of f when x equals a?
F of a.
F of a. And what would be the slope at this point? The slope to the curve y equals f of x at this point.
F prime of a.
Yeah, so the slope, so we have the point is a f of a. The slope is f prime of a. So the tangent line is y minus f of a is f prime of a x minus a, or y equals f of a plus f prime of a x minus a. And if x is equal to a plus h, yields y is f of a plus f prime of a x minus a, times h. So if you think about what's going on here, what's f prime of a times h over h? What's f prime of a times h over h?
F prime of a.
It's f prime of a. So this is just f of x minus f of a minus f prime of a. Well, we put the f prime of a over the other side, and it's just f of x minus f of a over x minus a equals f prime of a. So these are really the same. So another way of saying what does it mean for a function to be differentiable? It means if you subtract off the tangent line approximation, it's so good that even when you divide by a small number like h, it tends to 0. Well, we do a straight line in one dimension. What do you think we would do for a function of 2 variables?
Still a straight line.
Well, what do you think the generalization of a straight line is in? So in one dimension, we talk about a line. What do you think that would become if you go into one dimension higher?
Like a shape?
What shape do you think would be the generalization of a line? I want
A square.
a square, and what's a square? But it's got to be infinite. So the line is infinite. What do you think the infinite generalization of a line would be? So you were on the right track when you said square. What kind of shape? What kind of surface is? Okay, but I want it to be infinite. What do you call something that's infinite like that? You want to fly these when you go up. It's a plane, right? Equation of planes. So a line is this one-dimensional. So now in higher dimensions, you would have some kind of surface, and you would want to draw now some kind of plane, tangent to the surface at a point. So we have to figure out what's the equation of a plane. So for a line, how did a line work?
You
lost
hit the
the H.
back.
Yeah, I hit back. So the way a line worked is I gave you some point P, and I gave you a vector V, and then here was the equation of the line. So the point, x of t, y of t, say z of t, was just your initial point P plus t times your vector V, right? Now imagine I'm giving you a plane. So for a plane, I could have a base point. Let's call that base point P. And now a line had one direction. What do you think I'm going to need here? Two directions. So we could say maybe we have, here's one direction, let's call that V, and here's another direction, maybe W. It would be nice if they were perpendicular, but they don't have to be perpendicular. What's the only thing that must be true?
Must be like closed.
Well, if I want to get a plane, what must be true about V and W? What's the one thing I have to avoid where I'm not going to get a plane?
They're like 180.
Yeah, they're 180 or 0 degrees that they form a line. So I need V and W not parallel. So what do you think the generalization is of the equation? So we have x of t, y of t, z of t. If we're trying to do a plane, what do you think the generalization of the line would be? And do you think, well, actually think, do you think one variable is enough?
What do you mean?
So a line, what's the dimension of a line?
2D. I mean, what do you say?
Line is one dimensional. So if I give you one parameter t, that's enough. How many parameters do you think I need for a plane? Two. So I'll have maybe t comma s.
Really, the quadratic.
Well, I want, so the way it works is I move some amount in the direction of V and then some amount in the direction of W. I can get to any point on the plane like this. So how do you think the equation of the line generalizes? For the line, it was P plus T times V. Now I've got my
P
base.
plus T times V plus T times.
So it's P plus what?
TV.
TV, that's my first variable times my first direction.
Plus TS.
Well, T is how much I'm moving in the V direction.
Oh, then W.
So
Oh, no, SW.
Yeah,
Sorry.
SW. So this is a great way to do the equation of a plane. So you give me my base point, and you give me my two directions V and W, and I can get anything like that. Okay?
Yeah.
So it's actually not that bad to write equations of planes. Now, there is another way.
What would 3D be? Would it just be
So-
plus like
So
another?
if I had a hyperplane,
Would it just be like? Would it be like the same format? Then?
yeah. So
And like you'd add just like another variable,
Exactly.
another
they
thing,
sometimes
and
call
so
these
it'd be like
hyperplanes.
XW or something like that. Not XW, but like
Let's say we had x1 all the way up to xn. Okay.
Yeah.
So we would have, so for the line, it was one dimensionless, right?
where
A line was a one-dimensional object.
Yeah.
A plane is going to be a two-dimensional object. Do you want a plane in n dimensions?
Sure.
So we could have, t and s in n dimensions. It would still just be p plus t times the first vector plus s times the second vector. But we could also have a hyperplane. So this is a plane. But I could also have
like a cube or something.
x1, let's call it t1 through Tn minus 1, so one dimension less. And then Xn, T1, Tn minus 1. So it would just be P plus T1 V1 plus all the way down to Tn minus 1.
What if
Tn
you had
minus 1.
something like a cube? Would you just like add like another like
Well, we
cube or
talked about a cube in three-dimensional space.
Yeah.
And that would basically fill out the whole thing.
Right.
So it would be like, TV plus SW
plus like
plus
some
U,
third thing?
right? Plus maybe
Yeah, okay.
RU.
That's right. That was what I
Right.
was asking. So
Right. So normally you want to work with something that's at least a smaller dimension. So this would be one dimension less.
Yeah.
There is another way to do an equation of a plane. If I give you a plane like this, and I give you a point, okay?
Yeah.
And then let's look at some vector in this plane. Each plane has what's called the normal vector. And this normal vector is perpendicular to any vector in the plane.
Yeah.
Okay. So let's try to draw things in your
So
own.
it goes like straight up.
Right.
Yeah.
So here are my coordinate axes. And here is my vector P. Okay, that's my base point. Okay.
Yeah.
And then here, is my vector XYZ. Okay. So if I want to find the red vector, that's a vector in the plane. So red vector is in the plane. Well, I've got this, it's P to here, it's XYZ to here. So how would I get the XY, how would I get the red vector?
Sine. Well, signs are like cosine.
I've got two vectors, right?
Yeah.
How do I get this the other side? I want to use operations on vectors.
Yeah.
So if I have the vector XYZ, what do I have to do to it with this vector P to get this vector?
Subtract.
Subtract. So the red vector is just going to be, XYZ minus P is the red vector. Okay.
Yeah.
And this is perpendicular to the green vector. Right?
Yeah.
Now remember, we talked about before the dot product rule, that V dot W is the length of V, length of W, times the cosine of the angle between V and W. Okay?
Yeah.
What's true if two vectors are perpendicular? What's their angle?
Two vectors are perpendicular, 90 degrees.
Yeah. And so what's the cosine of 90 degrees?
0.
Yeah, so if V is perpendicular to W, have you used this notation for perpendicular?
Yeah.
Then theta VW is pi halves. So its cosine is 0. Right?
Yeah.
So if this red vector is perpendicular to the normal vector, what does that tell us?
0.
Well, what's 0?
The normal.
Okay, and what's related to the, well, it's not the normal that's 0. It's the,
So what?
so if
angle.
two vectors are perpendicular, their angle is 90 degrees. And what's the cosine of 90?
0.
So if two vectors are perpendicular, what do you now immediately know? If V and W are perpendicular, what must be true?
The cosine 0.
Okay, and what if the cosine is 0, what does that tell you? What else is 0? Well, look at the equation. What equation do we have that involves cosine of the angle?
Well, of course.
Look on this page. What equation do we have that involves? Look on this page. Where is there an equation that involves the cosine of the angle? Not,
No, this one, sorry.
what does that say?
That G times W.
That V
V
dot W.
would be 0.
And how do you take the dot product of two vectors?
I forgot.
That's when you multiply by components in an add.
Okay.
So this means, let's say the n vector, let's say that this is nx, ny, and z, okay? Sometimes we write this as ABC, just because it's a little bit easier. Okay,
Yeah.
so we would know that the normal vector dotted with the red vector, which is x, y, z minus p, what does this have to equal?
0.
0, is that 0 the number or 0 the vector?
Okay. All right, the number.
The number. So this means the dot product of a difference is the difference of the dot product. So it's n dotted with x, y, z minus n dotted with p equals 0, or a, b, c dotted with x, y, z equals n dotted with p. So what is ABC dotted with x, y, z?
AX plus BY plus CC, I mean.
Yep.
That equals.
We often call that D, just in terms of continuing the letters. But this tells us here's a way to find equations of planes.
Yeah.
So we have two ways to do it. One is I can give you two vectors and a base point. The other is I can give you the normal direction to the plane and a base point. How many dimensions does a plane have?
2.
2. So how many free parameters should I have?
2.
This looks like it's 3ax plus by plus cz equals d. I've got 3 values x, y, and z. Can I choose x, y, and z independently?
Yeah.
So I can choose any value for x, any value for y, any value
No.
for z. So once I choose x and y, do I have any freedom for z, or is z forced on me?
I mean, you have some freedom, but like it has.
Well, if I choose
pretty
x and y, I now know ax plus by.
So
and then,
Z is forced.
so z is forced. What does z equal?
D minus AX plus BY over C.
Yeah. What if I choose a and z? Is y forced?
Yeah.
Yeah. So really, even though it looks like there's 3 variables here, because I have one equation, one variable is always determined from the other 2.
Yeah.
And so this is how we write the equations of planes. And the reason equations of planes are so useful is what we were doing before in one-dimensional calculus, is we were trying to come up with a definition of the derivative.
Yeah.
You know, derivatives are useful. They tell us how things change. And we saw that an alternative way of writing the derivative is that when you subtract off the tangent line, it does such a great job that the error goes to 0.
Yeah.
And that's going to be how we're going to define the derivative in several variables.
Yeah.
Is that we want, when we subtract off the tangent line, the tangent plane, we want that to go to 0 as well.
Yeah.
So this is a good place to stop.